Okay, so hi everyone. Grateful to see you on the last day. Gopi, you're one of the organizers, right?
Yes.
So what that makes me. Okay, so we're very happy to have.
Very happy to have you all here. And so I'll talk about this generalization of MDS codes that we have been working on called higher-order MDS codes, and how we stumbled upon them and how they're related to so many different notions of optimality that people studied. These notions are stronger than MDS. So MDS are optimal for distance, but if you want some stronger optimality properties like list decoding, or we will see other notions, then it turns out all these different things are basically trying to find the same object, which is this higher order MDS code. So this is joint work with amazing collaborators, Josh, Manik, Visu, and Zihan, and it's based on a lot of works. So I'll try to say which result is from which paper, but may not always be correct. So the main result, the punchline, is this following result. So we show that generic Reed-Solomon codes. So what do you mean by generic? Think of Reed-Solomon codes where the evaluation points are chosen at random from a large enough field, are optimally list decodable. So here optimally means like really, really optimal. It means they meet the lower bound. This is called the list decoding singleton bound, which means you can list decode to L over L plus 1 times 1 minus rate with list size exactly L. And you cannot beat this. So what that means is, so list decoding, for people who are not aware, is that the code words, if you take any ball around any point of radius rho times n, then that ball should contain at most L points. And this rho is the list decoding radius. Okay? And so they are like optimally list decodable codes. So in this talk, I'll tell you our journey of how we got there. We started at a completely different point, and then somehow, go through different treasure hunt and finally, connect so many interesting islands encoded here.
Did ChatGPT do this for you?
Yeah, it is also DALI. Yes. Yeah, I think now they're integrated. Yeah. I mean, it gets, it got some text. I think this is its version of GMDS theorem, which is not legible to you, but it got some code stuff. It's still not good at writing text. Okay, so I'll only talk about linear codes in this talk. So a linear code n comma k code, I mean a k-dimensional code subspace of fq to the n. The rate is k or n, and we are interested in good distance, but we'll see that we'll need more than that. But the distance is the minimum weight of a non-zero code word. And then there are two ways to represent the linear code. One is via the generator matrix, whose rows form a basis for the code, or you can give the rows of the dual code. Or you can represent it by the parity check matrix, whose rows form the basis for the dual code. So these are the constraints that your code will satisfy. Okay, so MDS codes mean that they meet the singleton bound, which means the distance. So there is the singleton bound, which says the distance can be at most n minus k plus 1 for an n comma k code. And codes which meet this are called singleton MDS codes. So concretely, what that means is that if you take the generator matrix of an MDS code, which is a k by n matrix, any k by k submatrix should have full rank. So it's non-zero determinant. So that's what concretely it means. And we know how to construct them. Reed-Solomon codes do that, or fields of size n. Okay, so let's take a closer look at MDS codes. So let's say V is the generator matrix. So it's a k by n matrix. So and the columns are these vectors v1 to vn, which are k-dimensional vectors. And define V sub, if I give you a subset of the columns, define V sub A to be the span of the column vectors indexed by A. Okay, so it's a subspace of f to the k. And I'll use this notion of a generic matrix. So let's say W be by k by n generic matrix. What I mean is, think of it as a random matrix over an infinite extension field over the field you're working. Or you can think of it as a symbolic matrix with distinct variables. It doesn't really matter. So another way to write MDS thing is that any k columns of V are linearly independent. This is the generator matrix. Another way to write it is that the dimension of V sub A matches that of a generic code. So if I pick W to be generic, then the dimension of W sub A should be, the maximum possible, right? There are no non-trivial dependencies in this, so it should match that of a generic code, and it does. So that's what that's what an MDS code will do. So in that sense, MDS codes are behaving like generic codes or random codes. So can we push that further? So can I say if I take two such spaces, V sub A and V sub B, and I intersect them, will their dimension be the same? So it's like I not only want these spaces to have full dimension, but they also want them to intersect as minimally as possible. Okay, which is a natural thing to ask. So does that happen? So does the intersections of two such spaces also be as minimal as possible, which is that of a random code, like a generic code? And it does. So the proof is pretty simple. It's just inclusion exclusion. So you can write the intersection dimension as the sum of the dimensions minus the dimension of the sum. And the dimension of the sum is just the VA union B, because it's the span of vectors in A and the span of vectors in B, and you take the span again, that's just the span of A union B. And now each of them I can replace the V's with W because of A, because, and now I just recombine to get this. Great. So yeah, so we can go one step further. So now if I take intersections, they also behave nicely. Yes, exactly. So can we keep going? So can I get three wise intersections and say that they also behave generically? So I can try to do the same thing, which is like try to write this the intersection dimension using inclusion exclusion, and then combine the terms and then replace V's with W's and get this. So you see a problem with that? Yes, doesn't work. So the inclusion exclusion is wrong. It doesn't work for subspaces. It only works for sets. So this thing breaks down at 3 sets. So it works for 2 sets, but doesn't work for 3 sets, three spaces. Okay, so, and in fact, like this is apparently the top voted misbelief in math in Stack Overflow, that there is inclusion exclusion for vector spaces. So what that means for us is that you cannot express the intersection dimension in terms of the dimensions of V sub S. So therefore, this thing, the proof at least we had, kind of breaks down. So this between MDS codes and generic codes. So if you look at 3-wise intersections, they don't behave the same. Yeah, you can give a counterexample. Okay, so in our paper, this paper where we're studying maximally recursive tensor codes, we wanted these kind of objects, like codes which have these properties. I'll show you why we needed them, but basically we'll just ask, I call my code order M MDS, which is a higher order notion. If intersections of M spaces behave generically, they intersect as minimally as possible. Okay, so that is the definition. Very clean, very simple. Okay, so basically this M is like the order of approximation. As as M becomes bigger and bigger, it's like you get closer and closer to generic codes in some sense. This is some order X approximation to generic codes. And we have seen that order 1 and order 2 are the same as MDS somehow. But the MDS3 becomes the first non-trivial generalization. So you might ask, like, so this quantity here doesn't depend on W. W is some generic like code, so it only depends on the subsets A1 to AM. So can I write down an explicit formula for this in terms of the subsets? It only depends on the subsets A1 to AM and how they intersect with each other. It shouldn't depend on W. So can I write down a formula for it? And that's what we got stuck for a very long time. And finally, we figured out a really nice formula. So inclusion-exclusion breaks, but there is a way to still compute it explicitly, and this is the formula. So you partition your sets into, they're L sets. So you look at all partitions, and then you compute intersection of sets in each part. You sum them up, and you subtract some correction term. You take the max over all partitions, and that gives you the correct dimension.
That's not on stack exchange.
This is not on Stack Exchange, but we should put it there. but this only works for a generic W. So, and this is what we use crucially to prove our main theorem, and we'll see how this plays a role. Let's get a feel for this higher order MDS codes, and let's try to look at a concrete example, n,3 code. So it's a 3-dimensional code. So its generator matrix has 3-dimensional vectors as its columns. So because scaling the columns doesn't really change the property of MDS or the higher order MDS. I can always scale the columns so the first row is 1, or in other words, I can think of them as points in 2-dimensional projective space. So that's what I will think about. So I'll think of them as points in a 2-dimensional plane. And so these are my points. So what does MDS property mean? MDS means any 3 columns are linearly independent. That corresponds to the fact it is equivalent to saying that no 3 points are collinear in this representation. So we have these points. These points are my columns, and no 3 points should be collinear. That's an MDS code. So what is higher order MDS? What does MDS3 mean? It means the following thing. Firstly, they should be MDS, which means no 3 are collinear. And what the additional property is that now join pairs of points. So you join all pairs, and you get n choose 2 lines. So this is one line which is passing through 2 points, another line. These lines should also be generic. What that means is no 3 lines should intersect at the same point. Okay, so that's what. So it's one extra order of genericity that you would need. Okay, so can we construct such set of points in a plane? It's actually, we don't know how to do it optimally. So you can easy to prove that you need at least n square as a field size, because there are n points. You can draw n choose 2 lines, and any pair of lines have to intersect at a distinct point, right? So therefore, n choose 2 should be at least at most q square. So q should be at least n square. But we don't have a construction matching it. So the best construction we can give is q is n cube. So it's like a cube open problem. Okay, so now I'm going to connect this notion of higher order MDS to beyond MDS properties that people studied in coding theory. So so our journey started with this notion of MR tensor codes, maximally recoverable tensor codes, and that's where we started. So what are these codes? So these are basically tensor codes. So you tensor 2 codes, column code and a row code, and that's a tensor code. So what does maximal recoverability mean? So you take a tensor code. So for those of you who don't know tensor codes, it basically means that you look at 2 codes, and then you look at matrices m by n, such that each row belongs to the row code and each column belongs to the column code. So that's my code. So the set of matrices which satisfy these 2 constraints is my tensor code. And they have this nice locality properties. Like, for example, if this symbol is erased, or some few symbols in this column is erased, I only need to look at things in this column. But I have 2 ways to do it. One is like by the rows or the columns. So they have nice properties which become useful in distributed storage. So, for example, a tensor code is used in Facebook to store data. So what that means, what does MR means? It basically means that your code is optimal with respect to correcting erasures. Okay, so if I erase some symbols, then if some code with these parameters can correct these erasures, then my code will also correct it. Okay, so in that sense, it is optimal, globally optimal code, which can correct any set of erasure patterns that any other code can correct with the same parameters. And this was, so there is a notion of MR defined more generally prior work, but specifically for tensor codes, this was defined by Gopal and et al. In this paper. Okay, so how is that related to the higher order MDS property. So let's say E is some erasure pattern, so which means that this red region is the erasures. So let's look at its complement are the sets A1 to AM. So these are the non-erasures, and the red region is the erasures. And further, let's the column code be a simple parity check code. So it just has one constraint, just the sum of the things in each column is 0. So it's an m comma m minus 1 code. Then and let's say the parity check matrix of the row code is H. Then it turns out that this erasure pattern is correctable if and only if the dimension of the intersection of HA1, HA2, and HAM is 0. So what that means is if and so my code is MR if and only if this dimension is 0 whenever it is generically 0. So it means that if I started with the higher order MDS code for C row where the order is M, then I get an MR code. So to get an MR code, I just need to choose the row code to be a higher order MDS code of order M, where M is the number of rows. Okay, so that's the connection to MR tensor codes, and that's how we stumbled upon this definition, that this is the property we need for the row code for it to be MR. Okay, so that's what it's saying. So it's the tensor product is MR if known the row code is higher order MDS.
Can you say why is this true? This E is correctable if
It's not hard to see. Let me see if I can show that. So this is A1, A2, and so on. This is the errors. These are the things which I got erased. So I can only see things inside A's. So this is not correctable if and only if there is a code word supported in the erasures, right? And so it means I only see zeros, but there is a code word which has some non-zero support in the erasures, right? So what does that mean? So let's say these the code words are actually Y1, Y2 to YM. So the support of YI is an AI complement, right? So what that means is H, and these Y's are in the original code, in the row code. So HYI is 0. So and YI is supported here, so I can write it as YI is in HAI. Right. So and the sum of the YI's is 0 because I have a column check as well. What that means is I have vectors inside HA1 perp plus this so on HA and perp. A vector here, vector here, vector here, which is 0, which means they don't make the whole space, which is FQ, K, whatever. Which means if I take the complement, the dual of this, it means the intersection is non-zero.
They don't make the whole space because of sizes?
Because of the size. If you choose the maximal size, the sum of them is such that, yeah, you can, yeah, you without loss generality, you can look at. Okay, so now let's connect it to optimal list decoding. So what is optimal list decoding? I briefly alluded in the beginning. So you take as n comma k code. There is this list decoding singleton bound, which says that row should be at most L over L plus 1 times 1 minus k over n. And this is due to Shangguan and Tamo, and Ronnie Roth also had a prior work which kind of alludes to it. But this is the best you can achieve. In fact, so it's useful to study the average radius list decoding here. So what is average, I think, list decoding? It basically means, so rho comma L list decodability means that any ball should not have more than L code words, which means if I take L plus 1 code words, at least one of them should be outside the ball. And a stronger property is that if you take any L plus 1 code words, the average distance of any L plus 1 is greater than rho times N. So this is a stronger property which implies this. And this is a more, I don't know, nicer notion. Actually, this is exactly, turns out to be equivalent to higher order MDS. So the average radius is what we should consider. And actually, Ronnie Roth wrote a paper which is what inspired us to like connect these two things. So where he studies this average radius listed codable codes and which achieve this listed coding. Okay, so this is the notion of optimality that we are looking at, which are codes which exactly achieve this bound for average radius listed coding. So that's the optimally listed codable codes. So that's what I mean by that. And there are other notion of optimality, so this is a little bit harder to understand, but it turns out to be crucial to connect everything, all pieces of the puzzle. So this is called generic zero patterns. So so what do I mean by that? So what we are looking for is MDS codes which have constrained generator matrices. So you want an MDS code, but you want a certain pattern of zeros in it. Okay, so now the question is, when can you do it? And can you do it over small fields and so on and so forth? So I give you a pattern, a zero pattern like this. So I'm constraining that you should have zeros in subset A1 in the first row, A2 in the second row, and so on and so forth. The question is, if I start with an arbitrary code, or firstly, when is there an MDS matrix with that zero pattern? So there is a combinatorial condition that these sets should satisfy for even the existence of an MDS code. Because if there are too many zeros, like for example, if there are too many zeros in a column, then or like the entire column is zeros, then obviously you can't have an MDS property. Or if there are too many zeros in some region, then also it violates MDS. What you need basically is that if you take any k by k thing, there is a matching of the stars, like matching of supported on the stars, which makes that this determinant is not identically zero. So that is the property. And so it's a matching property. You can write the Hall's condition for it. So that is this condition. This is the Hall's condition that these sets should satisfy for every k-size subset of columns should have a matching of stars. Okay, so that's what we call by a generic zero pattern. A pattern which satisfies this Hall's condition, which allows the fact that you can have an MDS code with this zero pattern. Okay, so now this is the notion of optimality that we need. So we call a code ZZP or ZZPM in particular if it has a generator, if basically you can choose a generator matrix for this code with any zero pattern which has m distinct patterns of zeros. Okay, so this is called the order of the zero pattern. So for example, there are three kinds of zero sets here. So this is an order 3-0 pattern. In general, if my code, I can always choose a generator matrix which achieves any order m0 pattern, then I call it a ZZPM code. And they had applications to this. This is actually, historically, this was the first notion that people, other than list decoding, of course, but that people studied, which is they had applications in multiple access network and secure data exchange and so on, where they wanted MDS codes with these patterns of zeros. Okay, so that is this notion. Another way to think about it is I fix a generator matrix for my code. I can always do a basis change, which is like multiply it with the invertible k by k matrix and get all the any zero pattern that I want. So by multiplying with invertible matrices. Okay, so this is the other notion. So we have seen different kinds of beyond MDS generalizations, which is this optimally list decodable codes which attain all possible zero patterns in their generator matrices, and codes which are maximally recurrable tensor codes. And our main result is that they're all the same. And this is the same notion I showed in the beginning, which is about this intersection of these column subspaces. That is the main result in this paper. And it was very surprising to us that these are all connected and it's the same object. Okay, so more concretely, like you can give a very concrete, equivalence, which is like order m MDS is equivalent to attaining all order m zero patterns. It's the same as being optimally list decodable to list sizes up to m-1, but it's for the dual. So the original code is MDS, higher order MDS, if you know its dual is optimally list decodable. And it's equivalent to this MR property that I showed before. Okay, so I will give a little proof sketch now. And then the main thing is, of course, this formula that I showed you. So this formula is what makes all these connections possible. So how do we prove this formula? So the proof of this formula itself is one part of the equivalence. It basically it's the same thing. So what we need to show is this following thing, that ZZP implies higher order MDS, or you can show the other way as well. But let's just say concretely, this is what I want to show: that if my code, I can do basis change and get all possible zero patterns until order M, then I can actually, then my code is also higher order MDS, which means the intersections of the column subspaces should be as minimal as possible. So how do we prove it? So I want to say that this dimension is the formula I showed, right? So which is, or in other words, so what we'll do is we will give two bounds to this. So we'll give a lower bound for this dimension, and we'll give an upper bound also, and then show that these two are equal if my code achieves all zero patterns. So the lower bound is this quantity. So let me give some intuition why this formula makes sense. So what is this saying? So the dimension of, sorry, what? M is L, yeah, it's the same thing. So I want to say the dimension of V, so M is not, oh, sorry, yeah, you're right. This is M. M is at least the max over all partitions of M of S minus 1 times K minus, so the partitions has a S part, so that's what this is. Why is this a good lower? Why is this a lower bound? So the reason is, so let's first understand if everything is a different part. So that means that the dimension, it should be at least M minus 1 times K minus the sum of the sizes of these sets. Why is this true? This is just follows from this duality. It's because this, if I look at this dual of this, it's exactly the sum. And each of them have size. So this thing, the dimension of this is K minus AI, and the dimension of this is K minus AM. And if I add all of them up, there is still a gap left. They cannot make the whole space. Then that exactly is this dimension. So this is a trivial lower bound. But then how do I get all partitions? It's simply, I combine some of these parts, because this thing is always at least, if I intersect the corresponding sets I in P1, that's obviously in this, right? So sorry, it's not in this. It's in the, so this thing is contained inside the intersection of VAI, I in P1. Right? Because if I just intersect the sets, this is obviously contained there. And then similarly, if I had AI in P2, this contains the intersection AI in P2, and so on. And now I apply the trivial bound to these things, then I get exactly that. Okay, so this is kind of like a trivial lower bound that I can prove on the dimension of the intersection.
Sorry, why is it M minus 1 not M at the bottom? Like what? This is the point, right?
Sorry, what? Why is it? Mm-hmm.
There's M minus 1.
Oh, why is it that? Because you again want to do K minus the K minus AI. Yeah, you do a perp again. That's why you get a K minus again. Okay, so now we want to show a lower bound on this, which is, now this is where it gets a little interesting. So the lower bound looks like this program. So what is this lower bound trying to say? So the lower bound, how do I prove a lower bound on the dimension of VA1? Blah, blah, blah. So this is where the zero patterns come into play. sorry, that's the lower bound. I want to prove an upper bound on it. So how do I prove an upper bound? So let's say I construct a zero pattern with some delta 1 copies of A1 and delta 2 copies of A2 and so forth. And then I'll maybe have something left. So, and then like some delta m copies of AM. And then maybe there are some rows left over, which is k minus summation delta I. And so I'm going to impose that inside this, it has to be 0, and here you can have whatever, here you can have whatever, and so on. So if this is a generic 0 pattern, which means it satisfies my Hall's condition, then I can always do a basis change on V and get this pattern on it. Because V, for example, V is now, because V is a ZZP matrix, I can always do a basis change and get the 0 pattern. And note that it only has m different kinds of 0 patterns, 0 sets in it. So now if I do this basis change, now I can get a trivial upper bound on this. Because if there is a vector z inside this, then z restricted to the first delta 1 coordinates should be 0, right? And similarly, z restricted to the second delta 2 coordinates is 0 because z is in VA1, and VA1 has the first block 0. So then the first delta 1 coordinates of z is 0, the second delta 2 coordinates of z is 0, and so on. This is 0, and what is left is z restricted to this last bit, which can be non-zero. So therefore, the dimension of z can be at most k minus delta I. So the intersection has to be contained in a small subspace. So, and that's exactly this lower bound here. So we're trying to minimize this, and this is exactly the Hall's condition that you need to make sure that this thing is a generic 0 pattern. So this is a way to get an upper and lower bounds. And finally, the magic that happens is that actually you can prove via duality that these two are equal. So you need some this is not LP duality because these are integral. But it turns out actually if you write the relaxation for this and this, the LP duality implies the relaxations are equal, but the relaxation, it turns out because of the special structure, these LPs are integral. So the LPs correspond to the actual integral solutions. So that is basically the proof. It's I don't know. Actually, it is. The one way to prove it that I know. So in our paper, we prove it like really bare hands. We directly prove this combinatorially. But later we realized that there is this theory of total dual integral LPs, which uses there is a general theorem which says that if your constraints have some submodularity, then the LP is always integral. So you can also prove this directly via this general theory. Yeah, but it's a non-trivial duality. Okay. And the reason, like, we had this lower bound or this 0 pattern thing is actually this motivation comes from this paper of Gopal and Koparthi, where I don't know if Swastik remembers it, but basically here they need to understand which patterns are correctable and which are not, and you need to give a combinatorial condition on it. And to prove that some pattern is correctable, you need to give an explicit matrix. And the way they do it is by somehow instantiating some 0 pattern inside it, such that it happens. If you really dig deep into it and really understand it, this is what you get. Okay, it took us a while to understand the proof in a better way. They do it like a little more complicated. But this also gives a different proof for correctability patterns in the code. Okay, so I don't know how much time I have, maybe 15 minutes. So okay, so this is the main thing. So let me give a brief proof for how, okay, so I showed you ZZP and higher order MDS are equivalent. Now I need to show that list equalability and higher order MDS are also equivalent. So suppose not, suppose you have, so I want to show the contrapositive. If C is not optimally list decodable. So it's rho comma L list decodable when with rho is L times n minus k by L plus 1. What that means is there are L plus 1 code words whose sum of the distance is less than that. So L times n minus k. So, and let's say EI is the difference, the difference between CI and Y, which is the distance, which is the support. And the support of EI is AI, which is the sparse thing. So these sets, when you add them up, it sums to something small. Okay. And if H is the parity check matrix of my code, so what I'm going to do is I'm going to high level. So there's this bad list decoding configuration. There are too many points close to Y. So I'm going to create, I'll show that this bad configuration will lead to an intersection between subspaces of H, which this subspaces of H, like this HA1, HA2, which is more than the generic intersection. Okay, so that's my goal. So how do I do that? So just the fact that this, if I just multiply this equation with H times Ci is 0, so I get HEI is the same as HY. So what that means is these HE naught is EI is supported in AI. So what this means is that concretely, this I can write it as HAI times some quantity. So this vector is in HA naught, this vector is in HA1, and so on, right? So that's my intersection. So basically, the bad list coding configuration, if I just multiply everything with H, I'll get a vector which is in the intersection of all these subspaces. And my claim now is that this vector, which is there in all the subspaces, is a non-trivial intersection, which means this should not be there in the generic intersection. So that's what I need to show, which is that the dimension of this intersection is now greater than the generic dimension intersection. And the reason this is true is that because we have a formula for the generic dimension intersection, which is this quantity. And this quantity is attained for some partition, right? And this partition cannot be the trivial partition where all the parts are separate. Like, each index is in a different part. That's because of this quantities, right? So therefore, this, when I take each part to be separate, then this quantity is at most 0. That's what this is telling me. Therefore, it has to be a non-trivial partition which gives me this dimension. The trivial partition will give me 0 quantity here. So the non-trivial partition, which gives me a non-zero dimension here, and for a non-trivial partition, you exactly understand what kind of vectors are in this. These are vectors where some of the quantities are equal, but in my case, all the code words are distinct, so that basically kind of shows that this intersection dimension has to be greater than the generic intersection. So yeah, so on a high level, a bad list decoding configuration gives you a point in the intersection which is not there in the generic intersection. Okay, so we showed this equivalence. Now, how the main application is for Reed-Solomon codes. So for Reed-Solomon codes, the list decoding was kind of not fully understood. There is the Johnson bound, up to which we can list decode efficiently, but can we go beyond Johnson bound? That was not very well understood, except in some special cases. So people started studying like random Reed-Solomon codes, and can we list decode beyond Johnson bound? And there's a long line of work where they showed that yes, you can go beyond Johnson bound, but can we go all the way to capacity was not known. And we showed that you can go all the way to capacity. In fact, they are optimally list decodable, like meet the singleton bound exactly. So, and the main thing is this GM-MDS theorem, which basically says that Reed-Solomon codes attain all generic zero patterns. This was first conjectured by Dao Song Yuan and proved by Lovett and Yildiz and Hasebi. And now it is an immediate application. We get that Reed-Solomon codes are optimally list decodable because we proved that ZZP is same as all these, same as higher order MDS, same as optimal list decodability. Okay, so this is a brief history. So the first work is actually Dao Song Yuan, who conjectured the GM-MDS theorem for Reed-Solomon codes, which was proved in 2020. And then parallelly, there's this MR tensor codes, and our definition of higher order MDS codes comes from MR tensor codes. And then there was this conjecture of Shango and Tamo, who conjectured that actually Reed-Solomon codes are optimally list decodable. And Roth had another work where he looks at strongly list decodable things. And what we do is basically combine these three streams and show they are all the same, which implies, for example, implies that Reed-Solomon codes are optimally list decodable and optimal MR codes. Okay, so since then, there was a lot of progress. So let me talk about that. So we want to know, so there are these great codes, higher order MDS codes, but do they exist over small fields? That's the big question. Turns out, no, unfortunately, this was very disappointing. So we showed a lower bound that already at MDS 3, you need exponential field size, which is very surprising. What that means is if you want optimal list decodable with just list size 2, you already need exponential fields. That's sad. So what about if I relax it a little bit? So optimal list decodability is this exact list size, but if I really, okay with like 2 times that, can I get better? And then Guo and Zhang had this really nice work where they show you can get n squared field size if you just relax it a little bit, which was further improved to linear by Alrebia Goswami. And the main key insight is what Ray explained yesterday, which is that the slack will lead to your matrices becoming tall, and the probability of bad things happening decrease from 1 over q to the 1 over q to the slack, and you can union bound everything. This is great. So can we get even smaller field size? And yes, we can. So algebraic geometric codes, if you choose the evaluation points at random, you can get constant field size, which is exponential in L over epsilon, and this is more or less tight, except for the dependence on L, which is not known. And the way we prove it is by generalizing the GMMDS codes, GMMDS theorem. So GMMDS theorem says that if you pick a Reed-Solomon code generated matrix, I can do a basis change and get any generic zero pattern. But what makes Reed-Solomon code special? We still don't completely understand, but what we show is that actually any polynomial code will work. But maybe there is something much deeper. So you're saying that you can take evaluations of any polynomials as long as they're linearly independent. You can always do a basis change and get any generic zero. And this is also true for the dual code of such a code, which is not obvious, because Reed-Solomon codes are self-dual. But if you take arbitrary such polynomials, the dual doesn't have the same structure. So you need to reprove the GMMDS theorem for them as well. And even more generally, it's true for varieties. If you pick an arbitrary variety, irreducible variety, and then pick each column of your generator matrix as a generic point from this variety, that will also satisfy the GMMDS theorem. And this is what we used for the AG codes result. In fact, like C and the dual are also higher order MDS, and it's not easy to show. You have to show them both separately. Because there is even more subsequent work, which is nice. So Nogaransevi, Venkatesh, and Wouters, they had extended our work to multiplicity codes and folded Reed-Solomon codes, which do have efficient list decoding algorithms. But the construction, which means the evaluation points, are still random. We don't know how to. Sorry.
If you write anything, we cannot do linear.
Oh, you can do linear. That's great. So they. Okay. But S is like 1 over epsilon again.
Yeah, S is the folding parameter.
Okay. So folding parameter, which means like the alphabet size is n to the 1 over epsilon.
Yeah, but it's empty.
Okay, good. So then, yeah, okay. So the field, yeah, the alphabet is like here n to the 2 over epsilon then? In here, or now it is n to the 1 over epsilon. Okay.
And to the order of one.
Okay. Yeah, so that's some exciting new work. There is another work by Guo, Xiaoping Xing, Yuan, and Zhang, which is also really nice. What they do is they extended our whole framework to Gabriel encodes under the rank metric. So everything I talked about is the Hamming metric. Now the whole theory just applies verbatim to rank metric, which is really nice. So it's completely linear algebraic analog of the whole theory, just works as it is. Of course, there are difficulties proving it, but they managed to do that. So what that shows is that generic Gabriel encodes are optimally list decodable in the rank metric. So they prove a new GMMDS for this in the rank metric. So, and they have this beautiful formula, which is a generalization of the formula I showed, which is that, so previously we took a matrix and we took sub columns of it and then took its span, right? now what they say is, instead you can think of this W as a linear map from N to K, right? And then you apply to any subspaces of FQ to the N. So W sub Vi is just the image of this subspace Vi. Then these intersections of these images also satisfy the same formula. So it's a really nice extension of our work. Okay, so let me conclude with some open questions. So we defined this generalization of higher order MDS codes, and we've seen that they are connected to many things in coding theory, list coding, erasure coding, and so on. So the main questions are explicit constructions. Can we construct explicit higher order MDS codes? But here the catch is that you will need exponential field size, but it's still good to know what the constructions are. We don't have, even our exponential fields, we don't have explicit constructions. And you can ask about explicit Reed-Solomon codes or linear size fields which achieve the list decoding capacity. We don't know that. And similarly, edgy codes. We don't have efficient list decoding algorithms which go up to the list decodings up to capacity. So that's also open. And another interesting question is, like, can we extend this theory to list recoverability? Are Reed-Solomon codes optimally list recoverable? It's not just a curiosity, because list recoverability turns out to be really related to expanders and like optimal expanders and things like that. So if you have this result, it might, and you have explicit constructions, it will give you good pseudo-random constructions. Thanks.
Questions?
We don't even have the RS codes over polynomial size fields.
No, we don't. No.
We talked about edgy codes, you say it's at home, so
Yeah.
Combinatorial connection, MDS codes are sort of equivalent to maximal arcs and finite geometries. Is there any natural object that corresponds to higher order MDS codes, classical object in finite geometries?
So yeah, I'm not entirely sure, but I showed you this MDS3 example, which is some weird notion of generating.
Are around since the 1950s, the Italian school. Maybe they also know something about higher order.
Yeah, maybe that would be good to know.
So when you mentioned edgy codes, you talk about varieties, like varieties or like the usual curves? Like one-dimensional, or you mean?
Oh, so it is one-dimensional, but the theorem we needed for a variety. Yes.
It's easy to see Gabby-Dillon codes are not higher order MDS.
They are actually higher order MDS.
But then you have explicit construction.
Oh, but again, the alphas have to be random. So we know that generically they are higher order MDS, but not for fixed values.
Yeah, I meant fixed values.
No, I don't think they are higher order MDS. In fact, they are now, we know that because of their work of Go et al., we know they're also higher order MDS in this rank metric, which is a stronger notion.
Is there some generic de-randomization question that will help do all these explicit instructions?
I don't think so. Like maybe, I mean, I haven't thought deeply about how to de-randomize the proofs. Ultimately, there are exponentially many determinants. So you need to somehow, yeah, I don't, that's a really good question. Like, is there some object mean that will de-randomize this?
Maybe actually the question should be asked, addressed to those who have the result about the Gabby-Dillon codes. So how do you define that the generic construction, given that the variables have to be linearly independent in the
Right, right. So you choose any generic linearly independent.
So, the generic means that already the variables are linearly independent.
Independent, right, yeah.
Okay, so let's finish this.